So you can think of this as kind of projecting your measure mu onto the direction given by psi and then expanding it according to the magnitude of psi and then wrapping it around the unit circle in the complex plane before averaging. Some questions that you can ask about Fourier transforms of measures. So which measures mu are Reichmann? In other words, for which measures does the Fourier transform decay to 0 as the magnitude of the frequency grows off to infinity? And if the measure is Reichmann, then it's natural to ask whether it has polynomial or power Fourier decay, in which case, by which I mean that the magnitude of the Fourier transform is bounded above by some constant independent of psi times the magnitude of psi to the power of minus epsilon for some power epsilon. And this is, qualitatively speaking, in some sense, the fastest decay that you can hope for. Of course, you can ask about quantifying the power epsilon, but if you don't worry about that, then this is the fastest kind of Fourier decay that you can hope for. So the Riemann-Lebesgue lemma tells us that if a measure is absolutely continuous, then its Fourier transform is basically the Fourier transform of its Radon-Nikodym derivative. So absolutely continuous measures are Reichmann. And in this talk, I will be interested in measures which are singular with respect to Lebesgue. I'll be interested in fractal measures, and this is a topic which has been of great interest to many people ever since Erdős onwards. And if you're wondering why we care about Fourier decay of measures, and in particular fractal measures, well, it turns out that this has a very wide variety of applications in a whole range of different areas of maths. So we already heard an application this morning, actually, about sums of self-similar sets, but some more applications are fractal uncertainty principles. So these are, in some sense, fractal analogs of Heisenberg's uncertainty principle. So it says that a function and its Fourier transform cannot both be localized around fractal sets. Fourier decay can lead to Fourier restriction estimates, which is a very hot topic at the moment, about saying that the Fourier transform of an LP function can sometimes be meaningfully restricted to certain sets of measure 0. One can ask about the Fourier uniqueness problem. So if you're given a Fourier series, which sets will uniquely determine the Fourier series by its values on that set? And finally, normality of numbers. So if we recall, a number is said to be normal if its digits equidistribute in every base in a very strong sense. And we have no idea how to prove that specific numbers like pi are normal. But if a measure has fast enough Fourier decay, then we can say that almost every point with respect to that measure is normal. So these are just a few of the applications that we can get from our Fourier decay results by just applying existing results in the literature as black boxes. So for the rest of the talk, I'd like to forget about the applications and explain what is known about Fourier decay of various classes of fractal measures. So I'll mainly be working with self-similar and self-conformal measures. So let's suppose that we have an iterated function system of conformal contracting maps on some closed subset D of Rk. So by conformal, we mean that the maps locally look like similarity maps, but globally they might have a more interesting structure. And we'll always assume that not all of our maps share a common fixed point to remove triviality. Now, given a set of strictly positive weights pi, which sum to 1, the corresponding self-conformal measure satisfies this relation here. It's the unique Borel measure satisfying this. So the measure of any set is the weighted sum of the measure of its preimages. Sorry, there's meant to be a mu there. The measure of its preimages under the different contractions. And if all of our conformal contractions are in fact similarities, then of course mu is called a self-similar measure. And the theory of Fourier decay for self-similar measures is actually very interesting and subtle. So the first observation to make here is that the simplest self-similar measure you can think of, so this is the half-half measure on the middle third Cantor set, is not a Reichmann measure. Its Fourier transform does not decay to 0. And the reason for this is simply because the measure mu is invariant under 3x mod 1. So for example, if you look at the Fourier transform of our measure at a frequency 1, this will be the same as the Fourier transform at 3 and at 9, etc. So the Fourier transform does not decay to 0 as the frequency grows. However, almost every self-similar measure has polynomial Fourier decay, and this can be, there are multiple senses in which we can say this, multiple very strong senses. This has been known in various different situations since the work of Erdos and then Kahan, and then more recently, Solomiak showed that if you take a self-similar measure on the line and you remove a set of exceptional parameters of Hausdorff dimension 0, then your self-similar measure will have polynomial Fourier decay. However, very few explicit examples of this are known. If you take a Bernoulli convolution with a parameter that is a Garcia number, then it's been proved by Dai, Feng, and Wang that those specific self-similar measures will have polynomial Fourier decay, and some more examples have recently been constructed by Lauritz-Streck. But in general, if you give me a specific self-similar measure, it's very difficult to tell whether it has polynomial Fourier decay. Okay, so I'm going to bypass all of this difficulty to do with the algebraic and number theoretic properties of the contraction ratios by working with self-conformal measures which are not actually self-similar. So we're going to assume that we have some kind of nonlinearity in the IFS generating them. And a general principle that has been seen in several different settings is that if you have nonlinearity in a conformal IFS, then very often you should expect that that nonlinearity will result in the stationary measures having polynomial Fourier decay. So just a couple of examples of works that have proved results along these lines. Bourgain and Dyatlov considered Patterson-Sullivan measures on certain Fuchsian groups in hyperbolic geometry, and these are very closely related to self-conformal measures in one dimension, and showed that they have polynomial Fourier decay. And Salston and Stevens later generalized the result of Bourgain and Dyatlov to show that if you take a well-separated conformal IFS on the line, then and you assume a natural nonlinearity condition, then Gibbs measures will have polynomial Fourier decay. And a couple of remarks about these existing theorems. These use additive combinatorics. In particular, these two results use Bourgain's discretized sum product theorem. And they also assume separation conditions. And it's very difficult to remove the separation condition from these kind of results. But that's exactly what has been done in 4 recent papers. And we now have quite a complete picture of what happens for self-conformal measures on the line in terms of Fourier decay. So here's a theorem that we can get by combining four papers. If we take an IFS of analytic, so real analytic conformal contractions on 0, 1, let's say, and we assume that there's some index I such that the map SI is not an affine map, then every self-conformal measure for such a system has polynomial Fourier decay. And we don't need any separation assumptions here. So, yes. Analytic, real analytic, yeah. So we assume that there's some map which is not affine. So this is the weakest possible nonlinearity condition that you can hope for. But then we assume that all of our maps are analytic, which will somehow tell us that this non-affine map is very non-affine in some sense. And then we can see that every self-conformal measure has polynomial Fourier decay. And obviously one can ask questions about trying to reduce that regularity assumption. But the methods for this fundamentally rely on the IFS being analytic. So the proof of this splits into 2 cases, depending on whether the IFS is conjugate to linear or not. And by conjugate to linear, I mean that it can be written in this form F composed SI composed F inverse for some analytic diffeomorphism F and some affine contractions S sub I. In the case where the IFS is not conjugate to linear, there was a recent, the previous theorem was proved by Algom, Rodriguez, Hertz, and Wang in a preprint last year, and a very closely related result was proved by Baker and Salston independently and simultaneously. And a key step in the proof of this is to define a family of transfer operators depending on the conformal IFS and prove a spectral gap type result. So you prove some kind of uniform contraction result for this family of transfer operators, and then use that to get the Fourier decay for your self-conformal measure. In the linearizable case, well, this was tackled by Algom, Chung, Wu, and Wu, and independently and simultaneously by Simon Baker and myself in a preprint earlier this year. And the key observation here is that in the conjugate case, the measure mu is actually the push forward of a self-similar measure under the diffeomorphism F. And this is a nonlinear analytic map F. So really, this case boils down to showing that nonlinear push forwards of self-similar measures have polynomial Fourier decay. And there have been a few previous works along these lines, for example, a work of Kaufman, which doesn't seem to be very well known in the community, and then a more recent work of Mosquera and Schmerkin. But both of these results assumed that all the contraction ratios in the IFS are equal. And we might see a bit later why this assumption is quite important and why it's not so trivial to remove this assumption. So how about the two-dimensional case? And this is joint work with Han Yu now. So there are a couple of obstructions to Fourier decay in two dimensions that one needs to be aware of. So first of all, if your measure is reducible, and in this talk, when I say reducible, I'll just mean supported on a line in two-dimensional space, then we cannot expect any Fourier decay in a direction that is orthogonal to that line, because yeah, you'll be taking the inner product of two orthogonal vectors and integrating the exponential of that, and you won't get any decay. But there's a slightly less trivial obstruction as well, which is that if you take a self-similar measure like the Cantor-Lebesgue measure, which does not have any Fourier decay, and you then lift that up to the parabola under the map that sends x to x squared, then you'll get some measure on the parabola, which is actually a self-conformal measure, right? Because this lift is the restriction of a conformal map. Remember that conformal maps are just the same as holomorphic maps with a non-vanishing derivative. And this self-conformal measure that's supported on this parabola will have no Fourier decay in the horizontal direction, because the Fourier transform in this direction is just the same as the Fourier transform of the Cantor-Lebesgue measure in this direction. And we've already seen that that doesn't have any Fourier decay. So the main result here, I guess, is that if you discount these trivial obstructions and assume that your measure is not supported in any analytic curve, then we do have a similar theorem to the previous theorem. So let's suppose that we consider an IFS of holomorphic conformal contractions, and we assume that at least one of our maps is not affine. And we moreover assume that there doesn't exist an analytic curve which is simultaneously preserved by all of the maps. Then every self-conformal measure for such a system has got polynomial Fourier decay. This is very similar to the previous theorem, but we assume that no analytic curve is preserved by all maps. And once again, the non-conjugate case was proved by the same authors as before, so Algom, Rodriguez, Hertz, and Wang. And again, they use these transfer operator methods. In this case, it's a bit more complicated because we're in 2 dimensions, and they follow a recent, a paper of O and Winter to get the required spectral gap type estimates for the transfer operator. And the conjugate case I'm proving with Han Yu, and again, we realize our self-conformal measure as a push forward of a self-similar measure on the plane by the analytic map F. the case of higher dimensions, it's natural to ask about higher dimensions as well, but this is rather more difficult. So we do get some results for push forwards of self-similar measures from Rk to Rd, where k and d are arbitrary, and we can use this to deduce something about Fourier decay of certain conjugate self-conformal measures in higher dimensions. But to get a very clear picture, like in the 1- and 2-dimensional cases, I think will be quite a bit harder. And I mean, one of the difficulties that comes up again and again in different parts of the proof is that rotations commute in 2 dimensions and rotations do not commute in 3 dimensions and higher. And this causes quite a few difficulties. So how do we go about proving this in the, well, both of the theorems in the conjugate case? So remember that this now boils down to a question about nonlinear push forwards of self-similar measures. Well, let's suppose we have a self-similar IFS on Rk, and if the orthogonal parts of the contractions are denoted by OI, then you can count how many different compositions of n orthogonal contractions are there. So if this quantity grows sub-exponentially, then I'll say that the self-similar IFS is non-expanding. So in particular, if all your orthogonal parts commute, or if we're in dimensions 1 or 2, then we'll say that we're in the non-expanding case. So here's our push forward result, which implies the conjugate case of both theorems 1 and 2. Of course, the k equals 1 case was proved previously in work by me and Simon. Let's let mu be an irreducible, so not supported on any affine hyperplane, non-expanding self-similar measure on Rk. Let's let u be an open neighborhood of the support of mu. And let's let f be an analytic map from u into Rd. So this result holds for arbitrary dimensions k and d. Now we assume a non-degeneracy assumption on the function f, which is that we assume that the graph of f is not contained in any proper affine subspace of Rk plus d. So remember, the graph of f is some subset of Rk plus d. We don't want that to be contained in an affine subspace. Then the push forward of your measure mu under f has polynomial Fourier decay. Okay, so irreducible, non-expanding self-similar measure. You've got an analytic push forward of that by a map whose graph is not contained in a proper affine subspace. Then your push forward has polynomial Fourier decay. And a couple of remarks about this, that we've conjectured that this assumption of non-expanding can be removed, because if you don't have this non-expanding property, if anything, this might be likely to help you get Fourier decay, but the proof methods break down, so we can't prove that at the moment. And let me also remark that the decay here can, in some nice cases, be quantified. So in particular, if you take k equals d equals 1, and you take the Cantor-Lebesgue measure, and you push it forward under a nonlinear map, like the map which sends x to x squared, then Mosquera and Schmerkin got some bounds for the exponent epsilon of Fourier decay for that push forward. My method with tan u gives some better bounds, but the really interesting question, I think, would be whether these self-conformal sets that are realized by these push forwards are Salem sets. So are these measures, do these measures have the fastest possible Fourier decay that you could hope for? And we're still some way away from getting a bound that is strong enough to prove that these are Salem sets. Okay, so to prove this theorem, a key intermediate step relates to this quantity, which I'm going to call polynomial Fourier decay on average. So we say that a measure mu has polynomial Fourier decay on average if, for all epsilon greater than 0, there exists some positive delta such that the Lebesgue measure of the set of frequencies psi in Rk, whose norm is less than r, and for which the magnitude of the Fourier transform of mu at the frequency psi is greater than or equal to r to the minus delta, if the Lebesgue measure of this set of frequencies is small. So it's bounded by some constant times r to the power of epsilon. So what this condition is really saying is that the self-similar, well, the measure mu has power Fourier decay outside a very sparse set of bad exceptional frequencies. And this property of having polynomial Fourier decay on average is extremely useful. So in particular, there's a recent paper by Baker, Khalil, and Salston, which shows many things using this property of certain self-similar measures. And one of the things they show is that if a measure mu is self-similar and has this property, and it has some contraction ratios in the IFS r and r primed, such that the ratio of the logarithms of these contraction ratios is a Diophantine number, so it can't be approximated too well by rational numbers, then the Fourier transform of the measure mu decays logarithmically like this. So in some sense, you can use this property of polynomial Fourier decay on average to get rid of the bad frequencies at the expense of going to a slightly slower Fourier decay. So what's known about this property? Well, we would strongly conjecture that every self-similar measure that is not contained in an affine subspace has got polynomial Fourier decay on average. And I'm working on this at the moment. If a self-similar measure does have this property, then it's of polynomial Fourier decay on average, then it's certainly got to be irreducible, but the question is about the other direction. And this conjecture is known in very many cases. So in particular, the k=1 case was proved by Tsuji, and Tsuji's result was actually used by Algom, Chang, Wu, and Wu in their proof of the push-forward result. It's known when the maps have linear parts that are equal and without rotations. It's known for affinely non-concentrated measures by a recent paper of Osama Khalil. Okay, 1 minute. Okay. So in particular, this holds for doubling measures or measures which satisfy the strong separation condition. And with Han Yu, we prove this in the non-expanding case, which in particular covers the case when k=2. So Khalil's condition is not so easy to verify for self-similar measures because he had a different application in mind relating to proving exponential mixing for geodesic flows on certain manifolds. But I'm currently trying to go through and understand Khalil's proof and try to adapt his proof techniques, which use Hoffman's inverse entropy theorem in higher dimensions to prove this in all dimensions. Okay, so just very briefly, the proof in the non-expanding case goes by an Erdos-Kahan argument. So you iterate your IFS, you group together contractions which have the same linear part, and you then disintegrate your measure mu into lots of other measures which might not be self-similar, but which are somehow statistically self-similar. And the point is that each of these measures in the disintegration can be expressed as an infinite convolution of averages of delta masses. And when you take Fourier transform, this convolution becomes a product. So this is a product of averages of points which lie on the unit circle. And for the measure not to have polynomial, not to have Fourier decay at a certain frequency, you need lots of these terms to be small. So for lots of the terms, you need to have this clustering of the points around the same point in the unit circle on the complex plane. And the large deviation theory on this integration, together with an argument of Erdos-Kahan, says that with high probability, each of these measures in the disintegration will have this polynomial Fourier decay on average property. And one can use this to deduce that the measure mu itself has polynomial Fourier decay on average. And then once we have this property of polynomial Fourier decay on average, then to go from this to the push-forward result, what we basically do, it's very brief. Okay. All right, you look at the measure, you lift the measure to the graph of your function, and then you break it into pieces, and you show that most of those pieces will result in polynomial Fourier decay. Okay. So we don't deal with the expanding system, but there are works of Lindenstrauss and Bardeux, and then in Thomas Salston's recent paper about a recent survey paper about Fourier transforms and iterative function system that in fact get polynomial Fourier decay for expanding self-similar measures under certain conditions, like assuming that the dimensions are high enough. So being expanding should actually help you in the sense that you wouldn't even necessarily expect to have any exceptional frequencies at all. But the Erdős-Kahn method that we use just doesn't work in the expanding case.